So let me introduce you. And okay, welcome back everybody to our seminar series. Today we're pleased to have John Huerta that will be talking about bundle gerbes on supermanifolds. Please, the stage is yours.
Hi, thanks very much for the invitation. I'll be talking about bundle gerbes on supermanifolds, which is also the title of this paper on the archive. It's my pleasure to do so. But okay, so we'll organize this talk as follows. First we'll talk a little bit about what a supermanifold is. Then we'll talk about bundle gerbes. Both on and off supermanifolds. And we'll finish it up with a decomposition theorem, which I like to call the body and soul decomposition. These kinds of decompositions occur a lot in supergeometry, but this terminology is more from the physics literature. This is due to DeWitt. Okay, so what is a supermanifold? So the idea is that a supermanifold has commuting and anti-commuting coordinates. So you have the usual commuting coordinates, which pairwise commute with each other. And then you have anti-commuting coordinates, which pairwise anti-commute. So a function, it's not really a function, but the idea of a function of these two kinds of coordinates is that you can expand it in a kind of power series and if there are m x coordinates and n theta coordinates, then you should think of this power series as an element of the algebra where each of these coefficient functions is a C infinity function, say on R m, tensored with the exterior algebra with n generators. And this is our first example of a supermanifold. This is so the space with functions like this is the supermanifold Rm/n. And more generally, a supermanifold M is obtained by locally gluing these are m/n's. If it's of dimension m/n, of course. And so some properties that we have just from this definition is that we can always include the bosonic or even part of the supermanifold. And we're supposed to think of this, well, we're always supposed to think of this in terms of the algebra of functions. So it's actually this map. It goes the other way to this inclusion map. It's the map that sets the thetas equal to 0. There's also a map that projects out the thetas. And again, you're supposed to think of this going the other way in terms of the algebra of functions. So here, a function is just a smooth function of x. And here, it's just the same. It's constant in theta. So these two constructions, this one can be globalized. So every supermanifold has an underlying manifold that's included into it. This is an ordinary manifold, which we call the body. And this is our supermanifold. But this construction and this map, this inclusion map, is canonical. It's canonically associated to just the data of a supermanifold. But the map going the other way, the projection map, down to the body, this can't just be globalized from this prescription. You can kind of see why here, because we're treating the thetas, we're finding functions that are constant in theta, and being constant, you need something like a connection to think about it globally. So this, while it does exists, but not canonical. And in other categories, here we've been working with smooth functions. But in, say, if I was working with holomorphic functions, this might not even exist. P might not exist. I'll write in a very symbolic way. Are there any questions about supermanifold theory as I have presented it so far? Okay.
Sorry, John, maybe I could ask.
Yeah.
When you say you're gluing these spaces together locally, what are you gluing them with?
Right. Okay. So I wanted to avoid stating the definition, but I'm just
okay. Sorry.
I'll just state it. So a supermanifold is a topological space which is going to turn out to be this ordinary manifold MB with a sheaf. O of superalgebras, supercommutative superalgebras. and it's locally isomorphic to this supermanifold that I introduced at the beginning, Rm/n, which, by the way, is the first example of this construction. Rm/n is the pair where you have the topological space Rm, and then the sheaf. I'm going to write calligraphic letters for the sheaf of smooth functions tensor this exterior algebra. Does that answer your question, Mark?
Yeah, thanks.
Any other questions? Okay, so in this talk, I'm going to pick. So even though it's non-canonical, I am working in the smooth category, so it does exist. So I will fix a projection map to the body. But we'll only use it at the end. When we talk about the body and soul. And by body and soul, excuse me, I mean that what this projection map allows you to do is to divide up things like your functions on the supermanifold in a global way. Where this is just an ordinary smooth function. This is called the body of f. And everything that depends on these anti-commuting coordinates is the soul. And we'll see this theme running throughout this talk. But the reason that, that this allows us to do it, so P lets us globalize this coordinate construction because by providing a splitting of this short exact sequence. Where you have the algebra of functions on the supermanifold, which is a superalgebra, and you can pull all of them back to the algebra of smooth functions on the body, and that turns out to be onto. So it has a kernel, which is the soul part of these functions. And P provides a map that splits this short exact sequence. So it decomposes any one of these functions into a body and a soul. Okay, so now let's talk about bundle gerbes. So here's the slogan, which you're going to see fleshed out on this chart, which is that plus 1. So here's this, this hastily drawn chart of this. Maybe I should make this smaller. Actually, oh, chaos. Okay, I don't want to make this smaller. I'm not good enough at using this app yet. So if you have a line bundle,
on the top of
yes,
of your, you have 187%. So probably where you change it there to a smaller number, it will.
yeah, that's true. But then I make the page smaller. I like having the full page. Anyway, that's fine for viewing this chart. So given a line bundle on some base M, where M for the moment is just a smooth manifold, we can construct a characteristic class, which is an element in the second cohomology of M. And given a bundle gerb G on M, we can construct a characteristic class called the Dixmuir-Doughty class. This is an element of third cohomology. We can equip line bundles with connection, which locally is just described by a 1 form. We can also equip bundle gerbs with connection, which locally are described by 2 forms. And these connection structures have curvatures, which is a closed 2 form given by taking D of these 1 forms for a line bundle. And it's a closed 3 form for a bundle gerb. And these curvatures, this part I screwed up a little bit in trying to adjust the size of this chart just now. So in de Rham cohomology, these curvatures are closed forms, and they represent the classes of the characteristic classes in de Rham cohomology. So if we move the characteristic classes from integral cohomology to real cohomology, these forms represent them. And for bundle gerb, we can take the holonomy on surfaces, which is analogous to how for a line bundle with connection, we can take holonomy for curves in the base. So all of this generalizes to supermanifolds except maybe holonomy, because holonomy involves integration, and integration on supermanifolds is a bit subtle. So let's so why do we want to look at bundle gerbs? So for me, the motivation comes from Wessumino Witten models, which are a 2D conformal field theory, which are an example of a nonlinear sigma model. So the fields in a Wessumino Witten model are maps from a surface with metric to a Lie group, generally speaking. And so I'm going to assume that this is a compact, simple Lie group. But it could be reductive. And it could also be a supergroup, and that's the point of this work. So it could be a Lie supergroup. And on every compact, simple Lie group, there is a bundle gerb. And the thing that this bundle gerb does is, if you have your surface inside the Lie group ending on certain submanifolds, so this is sigma. Here's the boundary of sigma. And these submanifolds are certain submanifolds D. Then what the bundle gerb does is it takes this data of a map into G, such that your boundary lands on these special submanifolds, and it kind of gives you a black box and computes the holonomy of that map, which is a complex number. And then you can take these complex numbers and insert them into a black box that I don't understand, a black box from physics called the path integral. And you get the Wess-Zumino-Witten CFT. But I'm here to tell you about the first black box, about bundle gerbes. So what is a bundle gerb? Let's get into the definition. Are there any questions at this point? Okay. So now I'm going to let M be a supermanifold. A bundle gerb on M consists of the following data: a submersion over M, a line bundle L on the fiber square of this submersion. This fiber square is this pullback. and an ISO of line bundles called the bundle gerb multiplication. Which satisfies an associativity condition. So let's give the simplest example of a bundle gerb. Yeah, hey.
What are pi 1, pi 2, pi 3, please?
Yeah, that's a thanks. So this is over y cubed, the fiber cube of y. So that's pulled back. So yeah, so let me just say what y cubed is a little more explicitly. It's the fiber product over m of y with itself 3 times. And this has projection maps down to the fiber square. And these pi's are these projection maps. Pi I omits the ith
Okay.
factor.
Okay, thank you.
Sure.
And
So let me spell out what this condition says a little more clearly. In the case where, come on. So this map pi this map mu, sorry. So when you can think about fibers, which we can't necessarily do on a supermanifold because points are a little more fuzzy on a supermanifold, but in an ordinary manifold, so the fibers of L over the fiber square, they look like fibers over pairs. Where this is just a point over the same point in M. So then this map, mu becomes something like this. So mu being a map over pi over y cubed, that space consists of triples. So over the point x, y, z, mu is a map, an ISO like this. And let me give an example of a bundle gerbe. This is going to be an example of a trivial bundle gerbe. You fix a surjective submersion, a submersion. And you fix a line bundle T over Y. Not over the fiber square, but over Y. And then you choose your line bundle to define your bundle gerbe. Choose L equal to pi1 pullback of T tensor pi2 pullback of T dual. And construct mu from the canonical pairing. So in terms of fibers, which again doesn't always make sense over a supermanifold, a typical fiber of L looks like a fiber of T tensor its dual. Tensor the dual over Y. And then this map mu has to tell you how to take, well, we already saw what mu does. Mu pairs fibers like this and gives you points of the fiber over xz, but expanding these out, we can see immediately how it works. It just pairs. It just pairs the dual with itself canonically. Any questions about this example?
Why is it called trivial if there is a a non-trivial bundle coming in the construction?
Right. So yeah, that's a good question, and it's best answered a bit later in the talk. But yeah, I'll defer that question to a bit later.
Okay, thank you.
So a connection on a bundle gerbe which is the thing that we use to build these holonomies, consists of a connection nabla on the line bundle L and a two form, often called the curving on Y. Such that the following equation, called the descent equation, holds that the curvature two form of nabla up here on y squared is given by this pullback of B. And also such that mu is a connection preserving iso. Okay, so that's the data of a connection. And now let's get into the classification theorems. So before I state the classification theorems, I just want to note that bundle gerbes have all the usual operations. The operations we're used to with line bundles. Specifically, they can be tensored. If you have a pair of bundle gerbes, there's a way to tensor it and get a bundle gerb, and this is built from tensoring line bundles. They can be dualized. If you have a bundle gerb, there's a way that you can dualize it and get another bundle gerb, and this is built from dualizing the defining line bundle. And they can be pulled back. If you have a map of supermanifolds, M to N, and a bundle gerb G on N, then there is a bundle gerb F star of G on M. So I haven't defined, this relates to the question of why the bundle gerb defined from this line bundle is trivial, and I haven't defined what it means for two bundle gerbs to be equivalent, and I won't. But having these operations makes the set of equivalence classes of bundle gerbs on M. So this is equivalence classes. Bundle gerbs on M. Tensor makes this an abelian group with duals as inverses and these trivial bundle gerbs as the identity. And of course, we can also think about bundle gerbs with connection. So likewise, equivalence classes of bundle gerbs with connection, tensor makes it an abelian group. So, okay, so first theorem. So this original theorem is due to Murray and Stevenson. Murray was the person who introduced bundle gerbs, and he proved part of this theorem himself, but then the second half was in a paper with Stevenson. And for ordinary manifolds, and I have extended it to supermanifolds. So this abelian group, the abelian group of all bundle gerbs under tensor, of equivalence classes of all bundle gerbs under tensor, is isomorphic to third cohomology of the body of the supermanifold with coefficients in Z. And so to answer the question about why is the trivial bundle gerbe trivial, and the answer is it goes to the trivial class, to the 0 class in H3. And I should say that this this map is usually denoted, well, one way it's denoted is DD for Dixmuir-Daoudi class of the bundle gerbe. This is the analog of the turn class for line bundles for bundle gerbes. Any questions? So an important thing to note here is that for bundle gerbes without connection, it only sees the topology of the body. It only depends on the body. So having a supermanifold is almost kind of superfluous here. But this is not true for bundle gerbes with connection. They see some of the supergeometry. So again, this theorem is due to Murray and Stevenson for the ordinary manifold case, and I extended it to the super case. And it's also very much based on some related work that Bertram Costant did in supermanifold theory. So bundle gerbes with connection on a supermanifold M, that abelian group is isomorphic to Deligne cohomology. On the supermanifold, and Deligne cohomology is a cohomology taking values in complexes of sheaves. So let me describe this complex. You have the even invertible complexified structure sheaf. You have the sheaf of complexified one forms, and finally the sheaf of complexified two forms, but only their even part. So complexified even Durham complex. Okay, any questions here? And this operation that takes a bundle gerbe with connection to its Deligne class, I'll write as del of G. Okay, so let's get to the concluding portion of the talk, which is to do with the body and soul.
John, before you
Yes,
go
please.
on,
Yes.
sorry, is there a concrete relation between the two classifications?
Yes,
So,
absolutely. Yes.
Yeah, if you
there's
forget the connection,
there is a map. That just forgets the connection. And there's a corresponding map on the Deligne group, from the Deligne group into H3 of Z, H3 with Z coefficients.
I guess the map on the right-hand side is well known between the Deligne cohomology and the integral cohomology.
Absolutely, absolutely.
Okay.
It's just the map that forgets about these higher parts, the part in the 1 form and the 2 form. Then it just gives you this stuff in the structure sheaf. But due to a softness condition, this turns out to be the same as H3 with integer coefficients.
Okay, thanks.
Okay, so body and soul decomposition. So remember what the body and soul decomposition was about, that I need to fix this non-canonical map, which is this projection map, onto the body. And that allowed me to split this short exact sequence. The short exact sequence is canonical, but the splitting is not. Where I'm just restricting to the body in this step. But we can generalize this. We can generalize this splitting to the de Rham complex. So here's a proposition. P star splits the de Rham complex. Splits not, no, I don't want to say that. Splits this short exact sequence. Where I have a map from the full de Rham complex of the supermanifold to the body, the de Rham complex of the body. Again, this is onto, and it's given by restricting to the body, and it has a kernel. So P star provides a splitting of this short exact sequence. And what this means is that we can write that middle part of the de Rham complex as a direct sum. The de Rham complex of the full thing as a direct sum of the de Rham complex on the body plus this kernel. And moreover, K is acyclic. So closed implies exact in K. Any questions on this? In particular, degree 3, where the curvature of our gerbes will live, decomposes. So the curvature of a bundle gerbe with connection decomposes into these two parts, which I'll just denote as B and S. But it's closed. So that means that both of these parts are closed. And moreover, it's integral, not in the sense of integral forms from supergeometry, but in the usual sense that, that it lies in the image of H3 MB Z. And that implies that HB is also integral. So because we have this, this sole of the curvature that is closed, and that the complex of this kernel is a acyclic complex, that means that it has to be exact. So HS has to be d beta for some beta in K2. And because it's integral, we have the following fact. So theorem. I guess this is also Murray-Stevenson for the ordinary manifolds case, and then me for the supermanifolds case, which is that because you have this representability condition, that the Dixmuir-Doughty class is equal to the de Rham class of the curvature. This says that curve G is integral. It's also closed by construction. And conversely, if H is a closed integral 3 form, there exists a gerbe with curvature H. Okay. So we have two integral 3 forms. We have H and HB. They're the curvature of two gerbes. There's a gerbe G on M, which is a gerbe honestly in supergeometry. But there's also a gerbe GB on the body, which is purely a gerbe in ordinary geometry. And how do these compare? Well, they have different curvatures. The curvature of this is HB, the curvature of this is H, and those are not equal. They differ by this exact form. So how do we compare these? Well, we can use the projection map to compare them. So G versus P star of GB, again, these have different curvatures. I need to add in some 2 form to compensate for this beta. And I can do that. I tensor with the trivial with the trivial gerb that just has curving beta, and that will add a d beta to my curvature. Then these will have the same curvature. So same curvature. Are they equal or equivalent? And the answer is no. They can differ by a flat bundle gerb. You can tensor with any flat bundle gerb, and you don't change the curvature. So let G sub H nabla be the set of bundle gerbs with curvature H. Then there's a map going from the set of bundle gerbs on the body with the body of the curvature to the set of all bundle gerbs with the full curvature. And it's just given by this expression. You take GB to the pullback by P, tensor this correction, and this is an isomorphism of torsors over the flat bundle gerbs, which are the same on M and MB. That's the punchline of my talk, just in time. So, any questions?
Yeah, well, maybe. So is it probably easy to prove that you have always a connection?
Yeah.
Yeah.
It is, at least in the smooth super world. It's not that aspect is not different. I haven't thought at all about holomorphic supergeometry. I think that would be an interesting direction to go in with this work.
Okay.
Maybe I would have one question regarding the relationship between cohomology classes or integral cohomology classes and further cohomology classes with values of in a complex that if this classification of bundled gerbs with a connection is done only in a complex setup, or if it's possible to formulate the same relationship in a real world.
So these line bundles are complex line bundles, and that does lead to the the connections being given by complex one forms and the curvatures given by complex two forms.
Okay.
You can think about you can try to think about a Hermitian structure, and that's actually what is done for ordinary bundle gerbs. And then you have a Hermitian line bundle, and you actually have a U1 connection. So that's kind of naturally a imaginary form. And that's starting to get to where you can talk about real things. So yes, and that is also something I want to think about. I want to think about what a Hermitian structure on a complex line bundle over supermanifolds would be like. So yeah, I think that's a good question, and I don't really have an answer, but I want to figure it out.
Thank you.
John, maybe I wasn't paying enough attention at the beginning when you introduced the gerbes, but besides the base manifold M, you had this submersion from Y.
Yes.
So what is the role of this Y? So I think I missed that from the definition.
So the role of Y, so here's how I view it philosophically. Maybe you'll like this or maybe you won't. I view Y as basically, let me move back to the definition. So when you have this submersion Y, then you can construct a groupoid, which is just this groupoid, which is actually just this, the fiber square of Y over Y. This is a Lie
By the way,
groupoid.
what is the dimension of the fibers of Y? Is it?
So they can be the same as M, because Y could be like the disjoint union of a cover.
Mhm.
Like, so that's the main example of Y. That's the main example that you see in practice. Disjoint union, U alpha, a cover.
Oh, I see. I see. So it has to have some kind of resolution property.
Exactly. Exactly.
Okay.
Yeah. So what I think of the role of Y as being to replace M with an equivalent differentiable stack.
Mhm.
And then you build the gerb over that stack. So it is a kind of resolution. It's puffing your object M up to some looser object in a bigger category, in a two category.
At this point, maybe it would be also nice to relate this to original Mark's question, what he did at the beginning of your talk. And it's a observation that the gluing of patches you made from this colimate perfectly fits to the notion of collimating this resolution diagram. So once you have, for instance, in case of ordinary manifold, first two intersection collimate, you can get out of this diagram resulting supermanifold or manifold just by taking collimate of a union of your patches and the union of intersections, all intersections of
Yes.
your patches.
Yes, absolutely, yes.
So this is another perspective how you can glue patches to get resulting manifold.
Right, and another perspective on bundle gerbes is a sort of so Chatterjee and Hitchin also wrote some articles about bundle gerbes after Murray. Hitchin was Murray's PhD advisor. Is that true, or is it a Tia? Anyway, yeah. So one way to think of these bundles, when you have this, when Y is a cover, and these fiber squares are, like you said, the intersections. So I'll just write intersections by increasing the number of indices. And so you can think of a bundle gerb as being a line bundle alpha beta over each of these intersections. And then it satisfies a kind of co-cycle condition, which is given by this multiplication over the triple intersections. So yes, there's a very descent theoretic picture that one can take to this kind of data.
But John, does the choice of this y, does it affect does it not affect the classification? Like if you choose y to be something really wild, like, you know, have fibers of high dimension, you know, complex topology and so on, does that not affect the classification theorem that you gave at the end?
So you need to choose y so that it admits local sections, and as long as you do that, then it doesn't affect the classification theorem.
I see. Okay, thanks.
So you have a notion of an equivalence, right? And then you show that if you choose a different y, you get an equivalent.
Yeah, yes.
It works like in the usual case, right? I guess you pull back these two things to.
That's right. That's right.
To the product of y's and yeah. Okay.
That's right. So I basically define a. I really stick pretty closely to the original approach of Murray and Stevenson in this paper. So I define a equivalence to be a trivialization of G tensor H dual.
Yeah. Okay.
And a trivialization is then means that you can write it in this form, where we have this trivial bundle gerbe.
Okay.
And then crucially, where the multiplication just comes from pairing.
Yeah. So do you have some examples which would come from like trying to lift ordinary, super vector bundles?
Like a lifting bundle gerbe kind of.
Yeah, like a lifting.
So I haven't really thought about that. I'll tell you the main example that I had in mind for this. So main example, and I've got a paper that's about this. Yeah, that's right. The main example does not appear in the current paper. The main example is that I want to, so for G, Lie supergroup, one can build a closed three-form very analogously to how one does it for ordinary Lie groups. You take the supertrace of this expression in terms of the Moyer-Cartan form. And so this is closed. And it can often, but not always, often can be rescaled to be integral. So when both of those conditions hold, then I want to talk about the bundle gerbe H, G, such that the curvature of G is H. That was the main example I had in mind. And yes, it's entirely reasonable to think also about examples coming from obstruction theory as well. But because I was motivated by this Westphal-Witten picture, this is what I started thinking about. But yes, of course, from these theorems that I have stated so far, because you have a closed integral de Rham form, there is a bundle gerbe with that curvature. And moreover, it will have a decomposition like this into a gerb on the body pulled back by this projection and a 2 form, basically. And this decomposition looks surprisingly interesting for super Lie groups. I don't know. Yeah, those kinds of decompositions are the subject of the next paper that I'm writing about this.
Okay. Yeah.
So maybe I'll stop sharing. If there are any other
Yes,
questions,
Maybe.
yes.
if there are any
Sorry.
other questions, I'm happy to answer.
If not,
Maybe-
we can at least. Okay, sorry.
Maybe one short question from me. Isn't it necessary to want for morphism when you define bundle gerb from morphism from Y to the base to be surjective?
Yeah, so that's true. I just yeah, I was thinking of that as part of the meaning of submersion.
Okay.
That submersion, so a submersion in supergeometry, you can find this definition in Manin's book, for example. It's just something that's locally a projection map.
Yeah. Mm-hmm.
And then it's automatically surjective in any sense that you desire.
So I suppose if you would like to work it out, well, you may not like it, work it out, but if I would like work it out explicitly, like in terms of transition functions, cycles, or
yeah, I mean, so
my
like
transition functions will have body and soul, and
yes, they would, yes.
yeah, okay.
Yes, but the souls in some sense are always somehow acyclic.
Yes. Yeah. Okay.
But yes, those would they would be there, and they would be necessary for talking about the bundle gerb. So some other ideas that I have, besides working in the holomorphic category, where some of these constructions are obstructed, I'd
Yes.
also like to think about working over families. Like working over
Mhm.
families. In a family, there's not even really a good notion of body anymore. I mean, you can kind of get away with something, but then the body is no longer canonical.
Right.
And also, yeah, I have a bunch of questions about equivariance.
Oh yes.
Because this 3 form that I wrote down is invariant under the adjoint action.
Yeah.
So I wonder if it can be extended out to an equivariant 3 form, and then the gerb be extended to an equivariant gerb. Like the question of whether or not it exists is again a cohomological calculation, but I'd also be interested in explicit constructions.
So you mentioned holomy at some point, but then you said integration can be tricky. Did you think a bit about this?
No, but like one of the participants, Carlo,
Yes,
Cremonini,
exactly.
they're thinking about things like this, so I'm talking to them about it.
Okay, cool.
Okay, maybe we can stop the recording and give a round of applause for the very nice talk. So please unmute yourself.
Oh, thanks very much.
Thank you very much.